Hello and welcome to another discussion on our series on neuroscience and neural networks. Today we discuss backpropagation. The core idea is to update our weights, fine-tune them, set them up such that we get our desired outputs. So let's look at a solved example here and understand the essence of backpropagation and what it really does. This is our network. We have two inputs set up, and these are the particular data points that we are feeding into the network. These are the weights associated with these inputs, W1, W2, W3, and W4. These feed into the two neurons in the hidden layer, H1 and H2. And the output from these neurons is weighted into the output layer, okay, with W5, W6, W7, W8. These are the weights associated with these, and you get our output at the output layer with the output neurons O1 and O2. What I've listed here is our desired output. So this is the desired output 0.01 and 0.99, the target output that we hope to get should we feed these as inputs to the network, 0.05 and 0.1. Okay. We also have biases set up for every neuron, and those are set up as 1, but their weights are different. Okay, so 0.35 for the hidden layers and 0.6 for the output layer. Now we're going to make a forward pass on the network. We're going to feed in these inputs, get them multiplied by these weights, have them summed up as a net sum at the neurons, and then pass them through an activation function, which is sigmoid for our case today. All of the neurons will follow sigmoid activation function, and the output from that activation function in the hidden layer is then going to be used for the output layer. Okay, and then we're going to see if we have the output from the output layer as desired target or not. If there's any difference, we're going to see how big a difference that is. The goal, however, is to minimize that difference that we're going to get at the output. How do we do it? Let's step in. So let's keep our network here with us, and while we move around the equations. Okay, so that's the sigmoid activation function in general, and let's look at the output at the first neuron of the hidden layer, H1. Okay, so you have the input 0.05 multiplied by W1, the weight 0.15, right? That gets summed with this input feeding into the neuron, 0.1 times W2, which is 0.20, plus the bias, 0.35 times 1, then gets fed in to the first neuron. All right, so you get a net sum at the first neuron in the hidden layer that is then being used to compute, to pass through the activation function, and the output as a result is listed right here. In the same way, we figure out the net sum at the second neuron of the hidden layer, which after passing through the activation function comes out to be 0.596. Okay, so we have outputs at the hidden layers, and then these are being used with relevant weights W5 and W6 to find the output at the output neuron in the output layer. Okay, so net O1 then this after passing through the activation function. This is the out O1 that we have the output at the first neuron. Remember, the target was 0.01, but we happen to have 0.751, which is, and there's a lot of difference between this, which is of course a problem. And the same way we set up the net O2 and then the out O2, and that turns out to be 0.77. However, the target was 0.99. Again, a big discrepancy. So that's a problem that we have. So we need to have a metric. Basically, we need to have a parameter. We need to define our error so that we can minimize that as a function. So the error function that we typically do is sum of squared error. Okay, the idea is to sum the errors on both the new output neurons. The better representation is somewhat like this, where we basically are summing the errors on both neurons, but the error that we compute is squared. Okay, so it's summed, squared, it's an error squared. Notice, however, there is a factor of 0.5 or 1 by 2 in here. We'll see in a bit why we've plugged this in here. It basically helps us to make our computation easier at a later stage. However, the error from the first output neuron is target minus the output that we get, which was 0.75. Similarly, error from the second output neuron is the target that we hope to achieve minus the output that we got from the second neuron. Their difference is squared, multiplied by half. You get the corresponding errors. We sum that up to get the total error. That's the total error, and we hope to minimize this. But this is a function that we are hoping to minimize. The idea for backpropagation is that we're standing right here at the network towards the far end at the output, and we hope to propagate this error back into the network, where the goal is to minimize that error by assessing the contribution to the error by each weight in the network. Okay, so the error gets propagated back into the network all the way, and we hope to update our value of weights, because weights will impact the error at the end, and by updating these weights, by understanding their contribution to the error, we can minimize that error. Okay, so very intuitively this follows that since we are here at the network at the output, we begin with W5, then we're going to look at W6, W7, W8 to see the contribution of each weight in the error function, and we hope to update our weight accordingly. Okay, so for that we need to go ahead and compute a partial derivative, see how weight is impacting the error at the output for W5, 6, 7, 8, and then W1, 2, 3, and 4. And then we get these updated value of weights in a hope that these updated values are going to reduce the error. So let's go ahead and see how that impacts. We begin with the partial derivative of error total with respect to W5, and since there's no equation available to us that gives this or solves this directly, we take help of the chain rule, and we set our chain rule up such that we have these fractions or these equations available to us to compute them directly. So for example, net O1 and W5 are in fact part of the net O1 equation, so we could directly compute this partial derivative. Because W5 is in this equation, the coefficient of W5 is in fact the answer to this. The rest of them terms are in constants. So from here on we could find this directly. When we look at out O1 and net O1, this is also in fact a simple equation, equation of our sigmoid activation function. Because net O1 being in the denominator is inside the here function, we could derive this and find out the answer to this partial derivative as well. And then we look at the error total with respect to out 01. Remember our equation for error total, this function had target minus the output at the neuron squared, and then for the second one. So since we have out 01 and error total in this equation, we could derive this and find an answer to this, multiply them together to get this partial fraction basically. Once we have that, we could update our weight with this equation, where we just subtract a ratio of that partial derivative from the original weight and get an updated weight. There is a constant that is defining this ratio or impacting this ratio. We call it the learning rate. We don't want the learning rate to be too small, because This basically refers to conversation on gradient descent, where we want to achieve a local minimum in order to minimize the error, but we don't want the learning rate to be too small that it takes too long to get to that ideal value, and we also don't want this to be too large so that it skips past the ideal value. Okay, so we want to keep that a moderate value. In this case, we've taken learning rate to be 0.5 throughout, and by using this equation we are able to update our weight. So let's look at the computation of the individual partial derivatives for completeness. Let's start with this. Total partial derivative with respect to out 0 1, which is this equation. In fact, follows the simple power rule. Power comes down here, gets subtracted by 1, and when we take the derivative of the variable itself, the derivative for that is -1, gets multiplied here. See, the usefulness of having half here is that when this power gets multiplied here, 2 gets cancelled with 2. This is why we had half in our error function that we referred earlier on. When minus gets multiplied here, it becomes out minus target, and that pretty much simplifies our expression for this partial derivative. Just a simple example in terms of y and x, how power rule works. And then the next equation that we had was for the sigmoid activation function, basically. And this could be the derivative for this is slightly tricky, but again it follows the power rule. -1 gets multiplied here, power gets subtracted by 1. The internal what we have inside the brackets is net 0 1, but it's in an exponential, so it remains as it is. That being said, we get a -1 because of net 0 1 being right here. The coefficient gets multiplied right in here. And once that is done, there is slight manipulation into how I have my charger plugged in for the laptop. Yes, so once we have the power rule set up, there's a slight manipulation to make things simple, and that is to simply have the -2 come down into the denominator for this. Minus gets multiplied with minus, and that just goes away, and this is in fact out 0 1 squared. Okay, so we could write this as out 0 1 squared, and this term we need to see what can we do with this term. So if you look at the equation for the sigmoid activation function again, we just cross multiply them, so that leaves us with out 0 1 times 1 and out 0 1 times the exponential equals 1. We make exponential as a subjective formula, and that turns out to be this. Notice how this exponential is the same as that, so we just substitute this right here and basically cross out the squared with this denominator, and it leaves us with out 0 1 into 1 minus out of 1. So that simplifies our derivation of the sigmoid activation function. Basically, whatever is in the numerator, you're using that as a in the function. Okay, this gets very handy later on as well. Then the final term in our expression for the partial derivative was this. Notice how this is in fact the equation for net 0 1, and we only look at the derivative of w5 in this equation, which is out h1, and that is fairly simple to compute. We multiply these together, get a value for this, plug that into our equation for updating it, and it turns out to be 0.358. Okay, so that is in fact our updated w5. Now then, once we have this set up, we can move into w6. Notice, however, that for w6, it is still plugged in to the output neuron, the first neuron in the output layer. Okay, so pretty much everything remains the same, and apart from out h2 equation, because previously we were looking at, if you look at the third equation for w5, which was right here. So we were derivating it with respect to w5, but now for w6 we need to derivate this with respect to w6, so the coefficient of it is out h2. So other than that, w6 is pretty much, the rest of the terms are pretty much the same. Okay, so we get an updated value of w6. When it comes to w7, we need to understand that w7 is attached with the second neuron instead of the first. So that changes our equation slightly, because the error is now with respect to out 02 instead of out 01 for w7. Similarly, we are going to replace out 01 with out 02 and net 01 with net 02 here. Okay, with these new values, we could go ahead and use the simplified versions of our expressions. So wherever we had error with respect to out 01 as out 01 minus target 01, we just use out 02 minus target 02. Similarly, out 0, this is, remember, the derivation of the sigmoid activation function, so we just simply use the numerator in this to compute it. And with respect to net 02, we look at the equation of net 02, see the coefficient of w7 should be out h1, and if we could go back to see the equation for net 02, which was somewhere around, oh, we did not write that down. But if we just look at our network, the equation for net 02 should include h1 times w7, h2 times w8. So w7 should have an output from h1, okay, which is why we have this as a coefficient for our third partial fraction, partial derivative. And that being done, we move into w8, and w8 right here is again connected to the second output neuron, and this follows as before. We follow along the same lines, and we get an updated value of w8. The trickier part, however, here, that is w1, w2, and w3 and w4 that need to be updated. Problem with this is when we look at w1, notice how it gets some contribution from error 01 and error 02 as well. Okay, so when we were talking about w5, we only had contribution from error 01. We were talking about w6, only had contribution from error 01, but for w7 it was error 02. I am not sure if you noticed, but in the equations we are basically using error 02 because it's out 02 minus target 02, out 02 minus target 02 for w7 and w8. Okay, but here we need to know that there is a contribution of error total from, for w1, from error 01 and error 02, which is why we break the error total into two, error 01, error 02, and take partial derivatives with respect to out h1. Okay, out h1 because we're talking about w1. When we will talk about w2, yes, we will take out h2, but when it comes to w3 and w4, we'll be using out h2 in the denominator. Okay, that is very intuitive to understand. These are fairly simple to compute, the rest of the two, because this is a sigmoid activation function. We already know its derivative, and the net h1 equation is fairly simple. We only look at the coefficient of w1, which is input 1, and we just plug it in here. However, the first partial derivative is rather tricky because it involves both the error functions and their derivatives. So we compute them individually and sum them up. However, there's no equation that's available to us to compute this directly, so we form a chain rule for error 01 with respect to out h1, and in doing so we do get the second fraction because there is an equation that directly brings us this value, but there's no equation for error 01 with respect to net 01. So we use another chain rule to get that equation, and in doing so we get our equations directly. Okay, so there's a chain rule within a chain rule within a chain rule. Okay, so it's 3 layers down of chain rules. But these equations are there available. We break these down and we plug these equations back. This is for the first error function, and then for the second error function we do the same. Okay, we form a chain rule, see what equations are available to us, we get those directly. If we don't have a direct equation relating to variables, we form a chain rule in such a way that we get these equations directly available to us. That being done, we add these up together and then have them multiplied in the original chain rule to get our partial derivative with respect to W1. We do that and we update our W1 equation to get an updated value of weight. Similarly, we do it for W2. Remember, the second weight is also connected to the first neuron in the hidden layer, so it has contribution to both. But W2 is coming in from input 2. Okay, so there's a slight change which is reflected here in the net H1 equation. So W2 has a coefficient of I2, input 2, and that is pretty much what we need to change because the rest of it remains the same, and we could use those values to arrive at the updated value of W2. For W3, however, there is a slight difference because W3 is now connected to H2 coming in from the first input. Okay, so the first input reflects is right there, but the rest of the equations do change. We need to compute this partial derivative again, and once done we follow the rules as before. We add them and multiply them in the original chain rule, have our contribution of W3 with respect to the error total, get the updated value of W3. Once that is done, once that is done, we move to W4. We could make use of what we did in W3, and with that we could simply also see that W4 is connected to input 2, so that gets reflected here, and we could make use of the same value that we computed for W3 and get an updated value of W4. With all this discussion, we do get our updated values of weights. And remember, with the original weights, this is the error that we had. Okay, but with our new weights, we make another forward pass in the network. With our new weights, when we use our new weights with these same inputs to see if we now get our target outputs or not, turns out we don't, and the error is pretty much the same as before. So all that updating all those equations, and we've come out to have a similar error. Okay, excuse me. So what is the point then? The point is that it often takes more than one updating more than once, and turns out that if you update the weights 10,000 times in a program, the error gets down to as little as 0.00003. Okay, so that means that the output that you get is very much close to 0.01 and 0.99. So it takes a lot of iterations, but eventually the network does get to weights that are optimized, and they result in the correct output as desired, or the target output as desired, based on the given input. So in a nutshell, what we've basically done, we've found out the error at the output. We've seen how different it is from our target intended output, calculated that difference in an error function, and we've tried to see the impact of each weight in that error function. We've propagated that error back into the network and updated our values of weights. We've done only one iteration here, but if we do 10,000 times, we could reduce that error at the output to a very small number and get our output as close to the target as we hoped for initially. Thank you so much.